able to derive these wave equations to describe electric and magnetic waves and electromagnetic fields with sources. And we did this by introducing our new auxiliary fields A and phi, which we were able to successfully create uncoupled inhomogeneous wave equations to, as you can see here. And then we were able to derive these equations for E and, I should replace this with H, but E and H from our auxiliary fields that we created. So now we're going to actually see how we can use these equations that we derived to solve some systems with charges, right? So the first system we're going to look at, and we're going to try to find the electromagnetic field for, is of a singular point charge. So this is X, Y, Z, of a singular point charge, which pulses in intensity. So we can describe it as Q naught cosine omega t cosine omega t is equal to that charge Q. So it's kind of just like it's pulsing in the center. So the first thing that we want to do is, we don't really have any sense of source charge Q. We need to derive, using this, some kind of rho or charge density. And so the way we do this is we realize that this point charge, so everywhere else the field is zero. Only at this point charge is there a field at all. And so this is very reminiscent of something called, that you might be familiar with, called the Dirac delta function, which is Dirac delta function, which we describe as rho of x, or rho of whatever, but, sorry, not even rho, delta of some variable. Now, the Dirac delta function, you can kind of think of it, so delta x equals 0, where x does not equal 0. And the integral from actually minus infinity to infinity of the Dirac delta function with respect to x is 1. And so if I were to draw this function, I guess you could draw it as looking like this. And it's basically a way of describing like a singularity point, right? Because there's no like easy mathematical definition for it, so we describe singularities in this way using a Dirac delta function. And so we can use this Dirac delta function to rewrite Q as rho of x, y, z, t equals Q naught cosine omega t delta x delta y delta z right? Basically, that it's a singularity point in all these directions. And then from there, we can keep going, and we can say that rho of, we can describe it using phasor notation now, since we have that cosine, and we can say that rho of x, y, z, t is equal to the real part of the phasor rho x, y, z times e, j, omega t. And so here the phasor rho could be described as q naught delta x, delta y, delta z times, yeah. So similarly, we'll first solve for phi. So phi, we want to similarly define phi as a phasor to make the math easier. So we'll say that phi of x, y, z, t is equal to the phasor, real part of phi, phasor phi of x, y, z, e to the j omega t. And so then we can rewrite this equation here. We'll copy this. We can rewrite this equation now as gradient squared phi minus or plus omega squared mu epsilon. And this is because if you take the second derivative of this phasor, you'll see that it's just j omega times j omega, which is negative omega squared. So then this becomes positive omega squared mu u times phasor phi with respect to x, y, z, which I will write. And this is equal to minus q naught over epsilon delta x, y, z, or I'll just write delta vector r, right? Which is, again, the phasor for rho from there. Now, because we're working in spherical coordinates, since this is a point charge, we want to write this Laplacian using the spherical coordinate form. So the Laplacian in spherical coordinates is written as this expression: 1 over r squared partial over partial r of r squared partial phi over partial r plus 1 over r squared sine theta partial theta. This should be familiar to you. It's just a mathematical expression of the Laplacian in different coordinate system, but yeah. Plus, and you'll see that like quite a bit of this is redundant. A lot of it will simplify this really long expression, but I will write it out for the sake of showing you. But yeah, so this is basically the Laplacian in spherical coordinates as written here, and phi, but you'll see that this greatly simplifies because phi is independent of theta and omega. This makes sense if you think about it because the point charge only sends an electric field out radially. There's no change when you change with phi or theta, or sorry, omega or theta. It only propagates radially. So both of these terms end up canceling out, leaving us with an ordinary differential equation of 1 over r squared d over dr r squared d phi over dr plus the rest of this, I'll just copy paste it, is equal to minus q naught over epsilon. And so this becomes a very solvable, or actually, wait, one more step. So now when r equals 0, again, that's like the singularity case. We don't really know what goes on with the Dirac delta function at r equals 0. But for r greater than 0, so pretty much if we want to solve this solution for anywhere r greater than 0, we can rewrite this equation then as now a homogeneous equation, since anywhere else delta of r would just be 0, and so this entire expression would cancel out, and the right hand side would just become 0. And so this, what we have here, is a very solvable differential equation. I will not go into the derivation, but the solution becomes phi of r is equal to c over r e to the minus j beta r. Where beta squared is equal to omega squared mu epsilon. Cool. And then if you then go on to take a volume integral, you can calculate c as well. C equals q naught over 4 pi epsilon, so that phi of r is equal to q naught over 4 pi epsilon one over r e to the minus j beta r. And then if we want to figure out, if we want to turn this back into the time domain, or if we want to describe phi of r comma t, I should say, we can do what we usually do, which is multiply this by e, this expression phi of r times e to the j beta t, and then take the real part, and you would get the expression q naught over 4 pi epsilon times 1 over r cosine of omega t minus beta r. Which, okay, this is a pretty interesting expression if you look at it, because it basically is just like Coulomb's law, right? Because the voltage for as described with Coulomb's law is just q naught over 1 over 4 pi epsilon q over r, and then you would do r squared, q over r squared for e, but like this is basically just Coulomb's law, but now with this cosine value, because we're dealing with a pulsing charge, which is pretty interesting. And also another thing interesting is that this potential equation is a wave, is in fact a wave. It's a spherical wave because you have r instead of x, but it is a wave. It's not like a plane wave, it's a spherical wave. Which is pretty interesting, because what that means is that it's instead of looking at the E field and looking at the wave properties of the E field, we're now looking at the wave properties of the potential field, the energy, like which is what describes like the energy. And now you could keep going with this, and you could use this expression to derive E and H by using these equations. So we know that A here is equal to 0 because there's no current, it's just a charge. So that means that we know that in this point charge scenario, I'll write here, H equals 0. As for E, E is equal to the minus gradient of phi, which is equal to just the derivative with respect to r of q naught over 4 pi epsilon 1 over r cosine of omega t minus beta r. And if you take the derivative of this, you will get, or take the electric field, take the derivative of this, you will get the electric field, which I will not take the derivative of it, but if you want to, you can, and you can figure out what the electric field is from there. Cool. Thank you so much. So that was this is a simple introduction to how powerful this strategy of going through the auxiliary potential to then get the electric field is. We would have not so simply been able to achieve this if we had gone our previous route of just using the Maxwell's equations and deriving inhomogeneous electric field and magnetic field wave equations from them. So this shows the power of using this strategy to be able to figure out the electric field and the potential field, the electric field and magnetic field for more interesting scenarios. And so in the next video, we're going to look at instead of a pulsing point charge, we're going to explore what the electric field, magnetic field, and like the wave properties look like for a dipole current. So imagine like an infinitesimal current that just goes back and forth like this. This is what your like standard textbook dipole is described as. Like this is like the idealized dipole antenna is described as is this like small length of alternating current like this. And so we're gonna go about deriving the electric field and the magnetic field, and then also like as with that the potential fields of a system like this. So I'll see you in the next video. Thank you so much for watching. If you enjoyed, please like and subscribe and ask any questions in the comments. I'm happy to answer.